Hey everyone, and welcome to this Masterclass Explainer on optical communication. I am absolutely thrilled to have you here today. If you've ever wondered how data zips across the globe literally in the blink of an eye, you are in the perfect place. Today, we're going to unpack the fascinating world of optical fibers. Think of this as your foundational masterclass, where we take the complex physics of light and turn them into crystal clear concepts. Let's get started.
Here's a quick look at our syllabus for today. We're going to cover what optical fiber actually is, the anatomy of a fiber, how we classify them, dive into multimode fibers, specifically step versus graded, compare the types, and then finally look at real-world applications.
Okay, let's dive right into this. Section 1. What is optical fiber? The speed of light in a glass strand.
So at its most basic level, an optical fiber is a super thin strand, we're talking no thicker than a human hair, made of high-quality glass or plastic. But here's the real magic. Instead of transmitting info using pulses of electricity over clunky copper cables, optical fibers carry information using pulses of light. It's a simple shift, sure, but it completely revolutionizes how we transmit data.
Now, I want you to pause and think for a second. Knowing that these tiny cables use light to send data, where do you think we actually use optical fibers in our daily lives?
Well, if you guessed the internet, you hit the nail on the head. But it's not just the internet. We rely on them for our phones, cable television, and even really sensitive medical equipment. Why? Because they offer incredibly high speeds, massive bandwidth, and practically zero transmission loss compared to those old-school copper wires. Basically, when you need to move a ton of data without it degrading, you gotta use light.
Moving right along to Section 2, Anatomy of a Fiber. Inside the glass strand. If you were to slice one of these fibers open, you'd find three fundamental layers working from the inside out. Right in the middle is the core. That's the actual microscopic highway where the light travels. Wrapping around that is the cladding. And the absolutely crucial concept here is something called total internal reflection. The cladding basically acts like a mirror, constantly bouncing and trapping the light inside the core so it can't escape. Finally, wrapping the whole shebang up is the protective coating that shields all those delicate inner layers from physical damage, moisture, and dust. And honestly, these three parts are pretty much standard across almost all types of optical fiber. All right, Section 3. Classifying optical fibers. Light modes and refractive indexes.
So engineers basically use two primary ways to classify these fibers. Step 1 is looking at the number of light modes. Now, modes is just a fancy technical way of asking how many light rays are traveling through the core at the exact same time. Step 2 is looking at the refractive index profile, which basically means how does the light bend or bounce once it's inside that core.
Now, what's really interesting here is the sheer difference in scale. Let's talk about that first classification, the number of light modes. First up, we have single-mode fiber. This guy has a microscopic core. We're talking only 8 to 10 micrometers wide. Because it's so unbelievably narrow, only one single light path can fit through it. Then on the flip side, we have multimode fiber. Its core is much wider, typically 50 or 62.5 micrometers, which opens up the lane and allows multiple light paths or rays to travel through simultaneously.
Now, single mode is strictly the go-to for long-distance communication, while multimode handles the short distances. So, quick question for you. Why do you think having just one single light path in a single-mode fiber actually gives us better performance over long distances?
Well, it's all about keeping that signal perfectly clean. With only one path of light, there is zero interference from other bouncing rays. That means less signal distortion and virtually no modal dispersion, which is just that technical term for when different light rays arrive at the finish line at different times and scramble up the signal. Because single mode avoids that whole mess completely, it can carry signals over hundreds of kilometers without losing steam. That's exactly why it's the absolute standard for massive submarine cables spanning our oceans.
Next up, Section 4, Multimode. Step versus graded. How light travels. Remember that second way we classify fibers, the refractive index? Well, multimode fibers are split into two camps based on this. First is the step index fiber. You can kind of think of this like a hallway with perfectly flat mirrors for walls. The core is uniform, so when light hits the cladding, it bounces off sharply. It's violently zigzagging up and down as it travels, which unfortunately causes high modal dispersion. But then we have graded index fiber. This is a brilliant piece of engineering where the core's refractive index actually changes gradually. So instead of sharp, violent bounces, the light bends in these really smooth, sweeping curves.
So, thinking about those two distinct journeys, the sharp, violent bouncing versus the smooth, sweeping curves, which multimode fiber do you think gives us better overall performance?
It is absolutely the graded index fiber, and the physics behind this is just incredible. In a graded index fiber, the light rays that swing out wider toward the edges actually travel faster than the rays just shooting straight down the middle. It's such an elegant solution because it means that even though the rays are taking totally different paths, they all arrive at the exact same time. That drastically lowers your modal dispersion and massively boosts bandwidths. It's an absolute game changer for high-speed enterprise systems and local networks.
Okay, let's bring it all together in Section 5, comparing fiber types. Think of this as your ultimate cheat sheet.
Let's see how these three really stack up against each other. Single mode is without a doubt the reigning champ for distance and bandwidth, all thanks to that tiny core and single light path, keeping dispersion extremely low. Down at the other end, step index is basically your simplest multimode fiber. Its large core and sharp, bouncing light mean high dispersion, limiting it to short distances and lower bandwidth. But this brilliantly illustrates why graded index is so special right there in the middle column. It perfectly balances the extremes. You still get the easy-to-work-with large core of a multimode fiber, but because of those smooth, curved light paths, it manages to keep dispersion low, making it perfect for medium distances and high bandwidth.
Finally, Section 6, Real-World Applications, Connecting Our World.
These tiny glass strands are literally the foundation of our modern world. Single-mode fibers are the unsung heroes, acting as the massive global internet backbone and carrying our telephone networks across entire continents. Meanwhile, those graded index multimode fibers are the absolute workhorses, lighting up local area networks in our schools and offices, and handling the huge, short-distance data loads inside massive data centers. They even power highly sensitive medical imaging devices in hospitals, ensuring perfect, loss-free data gets right to the doctors who need it most.
So, as we wrap up today's explainer, I want to leave you with this thought. Knowing the brilliant engineering packed into these microscopic strands, how is the invisible light bouncing beautifully beneath your feet right now actively shaping your digital world? Every single text, every 4K stream, every random web search relies entirely on this hidden infrastructure. Thank you so much for joining me today. Keep learning, keep questioning, and I'll catch you in the next one.